Welcome! So right now I'm going to go into some more details on Lagrange multipliers. We're going to watch a little bit of this guy. Lagrange multipliers, geometric meaning, something like that. So let's get started watching this bloke.
Indeed, if I'm given some function, how do I know when that function is going to have a maximum, and how do I know when it's going to have a minimum? However, what we're going to do in this video is look at a special type of optimization, a special type of trying to find maximums and minimums. It's when I ask you to find the maximum or the minimum, but I give you a constraint, I give you a restriction. For instance, consider this graph. What I have is just the graph of some function, the function.
So he's about to look at this function subject to this constraint. So the constraint being x squared plus y squared equals 1, which would be the cylinder that you see up here. And so the surface that he's got plotted there is the same surface as I have plotted here in orange. F equals x times y plus 1. So it's just that the aspect ratios are a bit different in this. That mine looks flatter and his looks more shapy. All right, now this little curve that he's got here is the intersection of the cylinder or circle, if you think about this as it projects onto the xy plane. X squared plus y squared equals 1, but in 3D this is a cylinder, so that's this green cylinder here in this picture. Okay, so the question here that we're asking is, what are the maximum and minimum values along this boundary of this green circle?
xy plus 1. And the graph itself, well, it has a saddle point at the point 0, 0, but it then goes up in one direction forever and goes down in some other direction. However, if I impose a constraint, if I say it has to be on this particular curve, and I'm asking, what is the maximum of this function restricted to that curve? What is the minimum of this function restricted to that curve? The blue curve that I put up here, if I look at it in the domain of my function, is just the equation of a circle. X squared plus y squared is equal to 1. So in the domain,
that's looking down on this, right?
You are restricted to that circle. And then in the graph of the function, you look at, well, what does the function do above that circle? And the question is, what's the maximum of the function on the circle, and what's the minimum of this function on the circle? This video is going to talk about something called Lagrange multipliers. And Lagrange multipliers are going to give us a method to figure out the maximums of functions like these when you're constrained to specific constraints like this circle. For instance, I've highlighted here in the red dots the maximums of the value of the function constrained to live on the curve. And then in the domain, the two red dots say, well, where in the domain am I going to have these maximums?
All right, so on mine, let's have a look and see if we find that. It's not as clear because it's a bit flatter, right? So those red dots that he's put would be right here and right here, right? The top of this, right? So the maximum of this orange surface subject to the intersection with this green cylinder. And then the minimum values, if you look, the bottom is right down here, and then the opposite side over here.
Also looks like I have two minimums as well. To help me understand what's going on here, I put up contours on the graph of my function. Remember?
Okay, so the contours he's showing are similar to the contours I've got here. So remember, he's maybe calls these level surfaces, as some books do. But what these are is horizontal slices through the surface, and these blue curves that you see are those intersections of the horizontal slices of the surface. Have a look. At some point you can look through like you'd be peeking through some blinds or something, right? And these are contours, right? Contours or level surfaces.
What a contour is you telling me the height is constant. So I'm setting the function value, this xy plus 1, equal to various constants. And then I get these resulting curves. So for instance, if I set it equal to the value of z equal to 2, you get one curve. If I set it z equal to 1.5, you get a different curve, and so on. This gives you a bunch of level curves. And then if I want to, I can look at what these look like in the domain as well. Well, if I take the sort of bird's eye view and I look straight down, then I get this similar kind of effect. So I've got my blue circle.
Okay, so let's do that here. Let's take that bird's eye view and look down. So looking down on this, and I can sort of, not so easy, but I can turn it. Okay, so what he's talking about there is what these contours look like from the top-down point of view. So maxima and minima occur where these contours make a tangent with that constraint. So for example, you can see right here, they touch at a single point. Over here as well, they touch at a single point. Over here, they're touching at a single point, and over here, they're touching at a single point. So the tangent lines are, as I follow this mouse, these are the tangent lines there. Now, the point to bring out is that the gradient vector is perpendicular. So grad f, for example, is perpendicular to the contours, right? Remember what that does. The gradient vector points in a direction of how you would go to ascend that orange surface most rapidly, but it's also perpendicular to the contours. So it would be pointing, let's see, from this point of view, it would be pointing down, and from this point of view, it would be pointing up. And so when I said down, I should have been pointing this way, right? Because that's clearly down. Okay, and that direction is perpendicular to that contour right there. And so similarly, the gradient vector of this cylindrical surface is perpendicular to the surface. So these would have to be parallel. Okay, so let's go back and see what else this bloke has to say.
Restriction. And then the yellow curves are the level curves of the original function. For instance, if I take that z equal to 2, then I have this z equal to 2 looks like two pieces of these curves. And z equal to 1.5 is moving in a little bit, and so forth. Indeed, the way I compute these is if that the output of my function is 2, so xy plus 1 is 2, then that means that xy is 1, which means that y is just 1 over x. And so indeed, this curve here is just representing the equation 1 over x in the domain, and then it has the height of 2. Now, of all these different level curves, one of them is special. One of these level curves only just barely touches the restriction. Here, I'll focus just in on this one. This particular level curve has the property that this level curve goes right through what looks to be the maximum of...
Okay, so what he's talking about is right here, this level curve. I think I've been saying level surface, but level curve, or contour line, contour curve to the surface F. Right, so he's talking about this red point here, or this red point here, because these particular contours touch that green surface at a particular tangent point.
This function. And indeed, if I look at what happens down in the domain, that level curve, it comes along and just barely kisses the constraints. And this restriction that I'm choosing the particular level curve that comes in and just barely touches it, that's going to be my candidate to be a maximum or minimum, well, if it just barely touches it, it means something about the equation of tangent lines. In particular, what it means is that the equation of the tangent line to the constraint, the equation that's just a circle, the x squared plus y squared equal to 1, that's got a tangent line. And the level curve also has a tangent line, and if they come along and just meet, those tangent lines are the same thing. So at the two spots where this particular curve comes and just barely touches the constraint curve, then the tangent line is shared by both of these curves. Indeed, if I put all the curves back on here again, you see that this case is pretty special. You'll see that some of the level curves don't intersect at all, in which case they're just not relevant. They can't be part of that constraint. They're not even on the constraint. And then some of the level curves, they come in and they intersected at multiple places, but those values have lower values than the one that just comes and touches at the one spot. If you imagine sort of continuously varying the height as you move your level curves up, well, as you go up and up and up and up, at one point you just finally stop being subject to it. Indeed, if I took that special one, the one that's just come along and just kissed it, if I moved it even a little bit higher, it would no longer intersect the constraint in any way. It would no longer be relevant. So the one particular level curve that just comes and kisses it, that's going to be your candidates for maximums. And indeed, as we can see here, we also have minimums where it just comes and kisses it in the other direction along y equal to minus x, where it just kisses it. That's your candidates to be minimums. Okay, let's take this geometry and try to study it a bit more algebraically. So I'm going to return back to...
So he's basically going to say, and I think we've seen enough of this now, but he's going to say that the gradient vectors must be parallel, right? So in other words, grad f has to be parallel to grad g, and this is what gives you the Lagrange equation. Grad f is equal to the scalar multiple lambda, or Lagrange multiplier, times grad of g. Okay, so in other words, grad f is equal to lambda grad g, where this is a scalar multiple, the Lagrange multiplier. Okay, so let's go ahead and finish this problem off. We're finding the maximum value of this subject to this constraint. So what we want to do is calculate grad f, which in this case, we're differentiating this partially with respect to x first. And so we get y, and then differentiating this partially with respect to y, well, we get x. Now let's do the same thing for g. So we have 2x, comma, 2y. And so this equation right here is the equation, this vector, parallel to this vector, so scalar multiple times it. And if we expand this out and compare components, well, then it gives rise to this system. Y is equal to 2 lambda x. X is equal to 2 lambda y. All right, now we want to solve this as a simultaneous system. Okay, well, it's fairly easy in this case because we can eliminate one of the letters, say y. So let's sub that y in here. So substitution gives us x is equal to 2 lambda times y, but that is 2 lambda x. Okay, and now if we expand, then what we're looking at is 4 lambda squared x equal to x, but we got to be careful here. We've got x on both sides. We don't just want to cancel that. So let's write this as x minus 4 lambda squared x equals 0 and factorize so that we have x outside of 1 minus 4 lambda squared equals 0. So this shows the possibilities. Okay, so case 1, x could be equal to 0. And so if x is equal to 0, just looking at those, we would have to have y equal to 0 also. But considering the constraint up here, 0 there and 0 there, 0 does not equal to 1. So it doesn't satisfy the constraint, so this solution is no good. Okay, so we'll say contradiction. Case 2 is that lambda squared is a quarter, and so lambda equals plus or minus a half. So if lambda is 1/2, then what we're looking at is subbing into here 1/2, then y equals x and x equals y. And so subbing this into the constraint, we've got x squared plus x squared equals 1. So 2x squared is 1. And dividing by 2, we've got x equals plus or minus 1 on root 2. And since y equals x, y would be equal to plus or minus 1 on root 2 as well. Okay, now the last case, or it's a subcase of this, if lambda is minus a half, then y equals minus x, from this subbing minus a half in there. And so what that gives us then, when we sub that into the constraint, well, same story, we have x squared plus minus x squared equals 2x squared equals 1. And so again, x equals plus or minus 1 on root 2, but since y is equal to minus x, y is equal to minus or plus 1 on root 2. So in any case, we've got 4 candidate points for max and min as we expect. All right, so the 4 points are 1 on root 2, 1 on root 2, 1 on root 2 minus 1 on root 2, minus 1 on root 2, 1 on root 2, and minus 1 on root 2, minus 1 on root 2. Okay, so these are our 4 candidate points for maxima and min. So now how we find out which is which is we sub this into f. So f is equal to the product of xy plus 1. So taking the product of these, we've got a half for the product, right? So a half plus 1 would give us 3 halves. So this one is f equals 3 on 2. Right, that's that. And that would be the same story here. F is 3 over 2. Now, if the signs are different, then the product would be minus a half. 1 minus a half is a half. So here f is a half. And f is a half. So these are our minima. And these are our maxima. Okay, I want to show you a slightly more complicated example now. So let's scroll down here to a different case. So if we had f equal to x squared plus 3y cubed, and the constraint being that 2x plus 7y squared is equal to minus 4, so I'm setting g equal to 2x plus 7y squared plus 4, this part of it is the gradient vector of f. This part of it is the gradient vector of g. I've put in a third component of 0 so I can display these things as horizontal arrows or parallel to a horizontal plane. Okay, and then I am going to show this in a way that I can move the point around. All right, so let's go back to the beginning of t value. Now I've had to do this via parameterization of, I think I just need to run this again because I've done a different calculation. So there we go. Okay, so the pink curve or pink surface that you see is the cubic surface, the one with the power of 3 in it. And then this blue surface is the one with the power of 2 in it. And so the red arrow is the gradient vector along this curve of intersection of the two. All right, and the blue arrow there is the gradient vector of the surface G. So as I change t, you'll see that, hopefully you'll see, okay, maybe we need to sort of change points of view here, but you can see that that blue arrow doesn't line up parallel to the red arrow. All right, now if it's way down here, they're starting to be parallel, right? If I go this way. So that's where I achieved the minimum. But if I move this t value, that is a parameter in a parameterization of that intersection. And I understand that you haven't done parameterization yet, but this is how I was able to display it. Okay, so these are the gradient vectors. Now you notice there's becoming more parallel now as we're reaching the top. So as we're reaching the top, they are becoming parallel. Okay, so I hope that helps clarify the idea of Lagrange multipliers and optimization subject to a constraint.